I'm going to go through the independent t-test practice activity 2, the key, and kind of point out some of the common errors that I've seen and to go through the step-by-step process so you can compare what you did to what should be done. So if you'll notice the sentence that I have kind of highlighted here, the last sentence, it was in your active engagement. And it said using alpha 0.05, test whether invisibility had an effect on the number of mischievous acts for the data. Now, all it's saying is whether it had an effect. It's not saying whether mischievousness increased or mischievousness decreased. It's talking about an effect. So that is a two-tailed test. So the first thing you want to do is basically regurgitate that sentence as your alternative and null hypothesis. So I put the alternative hypothesis, if you'll notice right here, and I put H of 1, which is the alternative, wearing a cloak of invisibility will have an effect on the number of mischievous acts. So it's just this basic statement. Now the null is wearing a cloak of invisibility will not have an effect on the number of mischievous acts. So it gives you your independent variable, it gives you your dependent variable, and it's setting it up as a two-tailed test. So that is your step one. Step 1. Step 2 is setting the criteria. And this is where a lot of you, I noticed, had difficulty because you wanted to set this up as a one-tailed test. Because in your mind, you're probably thinking, well, obviously, if you're invisible, you're going to be way more mischievous. Well, that assumption is true, but nowhere in this research scenario is it stating that we're looking for more mischievousness with, invisibility. So we need to test this as a two-tailed test. So with our degrees of freedom and alpha 0.05, we get a critical value of positive and negative 2.074. So basically, if we draw that distribution out and at the ends, we have positive 2.074 and we have negative 2.074. Anything beyond in the tails is significant. Right down the middle is a 0, a t of 0. So anything that falls beyond those is significant. So now we can actually go in and start testing in step 3, which is the calculations. So as you notice, our t-test is the mean differences, mean 1 minus mean 2, divided by the estimated standard error. Now, if you notice at the very top, I calculated the basic calculations. So I always suggest you doing this so that you can have a reference to kind of go back and see, where maybe you went wrong. It also gives you something to communicate with me. If you're struggling and you just can't seem to be getting the right calculations, I'm probably, if you reach out for help from me, I'm probably going to be like, well, what'd you get for your sums of squares? And if you don't have those written with, the notations, I'm not going to know where you went wrong. So this is important to always kind of have this. So I have my no cloak group and my cloak group. I got the sum of x, the means, sum of x squared for each, if you notice. And then also the sums of squares. And I went through those calculations. So the sums of squares for group 2 is 40.25. The sums of squares for group 1 is 330. Oops, I'm sorry, that's wrong. That was the sum of x squared. See, that's a common mistake too. The sums of squares for group 1 is 30. What made me notice like that was a mistake right away is that the number 330 is so much bigger than the other sums of squares that is usually a major problem. So that'll give you a clue. And the means, it's very important that we have those means. So the mean for group 1 is 5, the mean for group 2 is 3.75. So now we have everything we need to calculate. Now, I did calculate the HOV to see if we met that assumption of variance. And I divided the smaller sums of square into the larger sums of square because they both have equal sample sizes. So we can just use the sums of square instead of variances. So we end up with 1.34, which means we met HOV because 1.34 is less than 2, which means it's less than twice the size of the smaller variance. So we can move forward, and now we can get our T obtained. If you notice, I already have my means, 5 minus 3.75, and then I need to get this estimated standard error of the mean difference. But to get that, I'm going to need to get my pooled variance, if you notice. And that's the sums of squares for group 1 plus sums of square for group 2, all divided by the degrees of freedom for group 1 plus degrees of freedom for group 2. Is what I do is I typically put parentheses around the numerator and then parentheses around the denominator so that I can keep my calculations accurate. So the pooled variance, I have it as 3.1932. If you notice, I'm sorry if this seems choppy, it's because I was interrupted. Be sure that when you're doing your calculations that you keep as many decimals as possible until the last calculation. That way there isn't a lot of rounding errors. So if you notice for the pooled variance, I have it as 4 decimals. And that 4th decimal, I am rounding appropriately so that I can make sure that we don't end up with rounding errors at the end. So once I get that pooled variance, you'll notice I plug it in, as you can see, SP squared over N. I plug it into the estimated standard error equation, and I divide by 12 because that's the sample size for group 1. So remember, you're only going to use the degrees of freedom in your variance equations, and that pooled variance, SP squared, is a variance equation. Once you get to the error equation, it is the actual sample size. So I have 3.1932 divided by 12 plus 3.1932 divided by 12. These are 2 separate fractions that are independent of one another. So I usually put in my calculator 3.1932 divided by 12, and then I times 2 because there's 2 of them. And then don't forget to take the square root. That's a common problem. So I ended up with 0.72952. So now I can plug that in to my denominator, and we end up calculating our test statistic T obtained as 1.7135. Now, 1.7315 is a positive number, so it's going to be to the right, but it falls like over in here. So 1.7135. It doesn't quite reach that 2.074. So it is not significant. It does not fall into those tails. So we know that's not significant, but we still need to finish our step 3 calculations because step 3 is all of the calculations. So I used Cohen's d, mean 1 minus mean 2, and 5 minus 3.75 is 1.25. And we're going to divide that by the square root of the pooled variance. So remember, the pooled variance is basically variance, but you're pooling it. So once you take the square root of variance, it's standard deviation. So actually Cohen's d is the same equation. It's the mean difference divided by the standard deviation. But in this case, it's the pooled standard deviation. So you take the square root of 3.1932, and I ended up with 0.6995, and we'd round that to 0.70. Not 0.7, but 0.70, because we have to have 2 decimals. So now we can move forward and do our confidence interval. And this is where I saw a lot of people having problems, a lot of difficulty with this. So you're going to take the difference between the means. So mean 1 minus mean 2, which we know is 1.25. and we're going to subtract it from the product of the critical T for a 2-tell test times the estimated standard error. It's not a 1-tell T, it's a 2T, and it's not the obtained T. It is the critical value. So 2.074 times 0.7295. You're going to subtract that product from 1.25, and you should get negative 0.26. And then you're going to add that product to 1.25, and you should get 2.76 for your lower boundary and your upper boundary for those confidence intervals. And now you can go ahead and write those APA results. The APA result is very important. And this seems to be where some of you are really struggling, is writing those results or determining whether it's significant. Now, really, ultimately, it's, does the test statistic fall beyond that critical boundary? And 1.7135 does not. So we did not have significance. So I would basically regurgitate my null. You know, aware in a cloak of invisibility did not have a significant effect on the number of mischievous acts compared to no cloak, as this is your T, and the degrees of freedom you use to look up your critical value equals 1.71. Your T obtained should be rounded to 2 decimal places. It's not 1.7135, it's 1.71, because that 3 keeps it as a 1. If it was 5 or greater, it would go to 1.72, but it's not. And then comma, P is greater than 0.05 to tell. Now we know that P is greater than 0.05 because out here, it's in these tells, it's going to be less than. So kind of go like this. Here's your alligator, basically. If your test statistic falls on this side, it's at the mouth, and that's where your P would be. So P would be greater than alpha. Alpha is out here in these tells. So P is greater than alpha, 2 tell, and you would list your alpha, your Cohen's d, and the 95% confidence interval. It's all one sentence. It's very important because this is a language. This is how we communicate results. You need to learn how to not just communicate the results, but read the results. You want to make sure that, you know, with research, you're understanding the language of the research. And that is what this is weighing the importance of, is that language of reporting results. So if you have any questions about this, please let me know. Hopefully this was helpful to go through something that you've already done.